This screencast talks about how to do Part C, Question 2A and B of the Capstone project. So I'm on page 13 of the Capstone package, and it says we need to start making the Visual Python simulation. The first thing we need to do is to make spheres to represent the 4 objects that are moving: the Sun, the Earth, the spacecraft, and Mars. Remember the coordinate system used by Visual Python. The origin is located in the center of the screen. The positive x goes to the right of the screen, the y-axis runs vertically upward, and the z-axis, the positive z-axis, points out of the screen toward you. Everything that we're doing is moving in the xy plane. In all cases, you can leave the z-coordinate equal to 0. Also, we don't explicitly put any dimensions into Visual Python, but the code assumes that you are working in a consistent set of units, and it will scale everything accordingly. And in our simulation, we are going to work in terms of astronomical units. So when we create the spheres, those objects are going to continue to exist for the entire duration of the program, and they will always be displayed. As you update the attribute of an object, primarily you'll be updating position to make things move. Every time you update position, VPython will automatically redraw the object to display it with that new value of the attribute. Here is an example of how to create one of the spheres. You could go back to some of the activities that we did last fall and copy, if you want, one of the sphere creation lines and bring it into your new program. Here is an example for creating the Earth. So first you have to give it a name, and here I'm calling my sphere that represents Earth, I'm just calling it Earth. Set it equal to sphere, that's the name of the class of object that we're creating. And then there's a list of attributes. Notice that all of these attributes have to be contained in a set of parentheses, and there's a comma that separates every attribute. The first attribute here is position, which is POS, equal, vector, and then in a set of parentheses, I'm giving the x, y, and z coordinates of the center of this sphere. Radius is telling the size of the sphere. Remember, this is in astronomical units. Color. Make trail is an attribute that will cause the object, for example, it's almost like dropping breadcrumbs. As it moves, we'll be able to see the path that it moved along. And so I want to set make trail equal true, and I'm giving the trail type equal points. That way it will make a dot at each position as it moves along. Another trail type is line. Personally, I prefer the points attribute. Interval is the frequency that it drops that breadcrumb and draws that trail type point. And so I'm doing it every 10 days. And then, of course, you can give the trail color. It could either be the same color or a different color from your sphere. All of this code is on a single line in your Visual Python program. Here, it's running into 3 lines because I have made the text large to make it easier to read. But all of this is one line of code with no returns or anything like that. When you create your 4 objects, you should see something like this. The yellow sphere here is representing my sun. The turquoise sphere is the Earth. The red sphere is Mars. I also created a sphere for the spacecraft, but you'll notice that right now I do not see it because you want to create the spacecraft and the Earth at the same position initially. I understand that's an approximation, but so when you first create them, they're at the same position. But then as time goes on, once we begin updating the positions of these objects, we'll start to see the spacecraft moving relative to the Earth, and so it will show up soon. Okay, so that was part A of question 2. Part B, which is on the next page, it says identify all of the constants that you're going to be using in this computer program. So we want one section that identifies our constants. That way, if we need to update anything, we only have to update it one place. In this package, I've given you tables that identify the types of constants that you need to specify, as well as the units and things like that. So you should fill out this section of the student packet, but I'll just show you what a section of these constants would look like. So this is the list of them. There are quite a few constants that we're using in this program. Each one of these I've given a name, just a short name that represents that constant. You will need to be sure to use that same name for that constant throughout the program. I've given you a few of them here. You should definitely say t equals 0. That's the initial time. dt equal 1. That's the time interval, and we're going to work with time intervals of 1 day. Notice that as I identify these constants, I've gone a little bit to the right and I've put a comment for each one to explain what it is. I wanted to use short names for my constants just to make the typing easier, and that makes it especially important to put a description of what this constant is into the code. So you start the comment with a pound sign and then just describe what that constant is. For example, in my code, I used HE and KE as the X coordinate of the Earth's center and the Y coordinate of the Earth's center. But anyway, so you can make up your own names. You don't have to use mine, but you really should put some description. That way, if you go away for a few days, or if someone else is looking at your code, they'll be able to decipher it. Also, at the bottom of this list, there are two other constants that we should probably just agree on. Theta is going to be the initial, or it's going to be the angle that we use to calculate the ellipse x and y coordinates, and I initialize that with a value of 0 degrees. And d equals 0, that's going to be the initial constant that is used to calculate the ellipse x and y coordinates.